Hello, welcome to this particle physics course. Today in this lecture we will discuss about the Higgs boson, the recent discoveries of Higgs boson, the mechanism of the Higgs field, as well as the properties. In this lecture we shall discuss about the electroweak interactions and the Higgs mechanism. After this course you will know how Higgs boson is produced in the LHC, how we identify its production and decay, verification and quick review of our standard model, pathway to multiverses or supersymmetry. Now let us start with the topic, what is Higgs? The Higgs field is a microscopic field that must be quantized. There is a particle which corresponds to the phi field, the scalar Higgs boson H naught. All its properties were known before it was discovered, except its existence and its mass. In particular, its branching ratios into different fermion-antifermion or boson-boson pairs are fixed once the mass is known. Here are few Feynman diagrams showing the production of the Higgs boson. So this brings us to our next topic, how can Higgs be produced? The Higgs boson can be produced as a real particle at a hadron collider, provided its energy is sufficient. This is the case for the LHC. From the previous Feynman diagrams, we have shown the formation process of Higgs. The existence of Higgs boson has been confirmed in a spectacular way by the experiments ATLAS and CMS at the LHC in 2012. Now let us understand the Higgs mechanism. Following the 1962 and 1963 papers, three groups of researchers independently published papers in 1964 with similar conclusions: that the conditions for electroweak symmetry would be broken if an unusual type of field existed throughout the universe. And indeed, one result would be that some fundamental particles would acquire mass. The field required for this to happen, which was purely hypothetical at that time, became known as the Higgs field after Peter Higgs, one of the researchers, and the mechanism by which it led to symmetry breaking known as the Higgs mechanism. A key feature of the necessary field is that it would take less energy for the field to have a non-zero value than a zero value. Unlike all other known fields, therefore, the Higgs field has a non-zero value or vacuum expectation everywhere. It was the first proposal capable of showing how the weak force gauge bosons would have mass despite their governing symmetry and while keeping a gauge invariant theory. Although these ideas did not gain much initial support for attention, by 1972 they had been developed into a comprehensive theory and the time and proved capable of giving sensible results that accurately describe the particles known at discovering during the following years. During 1970s, these theories rapidly became the standard model. There was not yet any direct evidence that the Higgs field actually existed, but even without proof of the field, the accuracy of its prediction led scientists to believe the theory might be true. By the end of 1980s, the question of whether or not the Higgs field existed, and therefore whether or not the entire standard model was correct, had come to be regarded as one of the most important unanswered questions in particle physics. Now let us understand, what do we mean by the Higgs field? According to the Standard Model, a field of the necessary kind, the Higgs field, exists throughout space and breaks certain symmetry laws of the electroweak interaction. The existence of this field triggers the Higgs mechanism, causing the gauge bosons responsible for the weak force to be massive, and explaining their very short range. Furthermore, it was later realized that the same field would also explain, in a different way, why other fundamental constituents of matter, including electrons and quarks, have mass. However, for many decades, scientists had no way to tell whether or not the Higgs field existed, because the technology needed for its detection did not exist at that time. If the Higgs field did exist, then it would be unlike any other known fundamental field. But it was also possible that these key ideas, or even the entire Standard Model itself, were somehow incorrect. Only discovering whether the Higgs field existed, or if not, what else was breaking the symmetry, would solve the problem. Since every field has a field particle, our Higgs field also do have a field particle. This field particle is called as the Higgs boson. So let us now know about what is Higgs boson. The hypothesized Higgs mechanism made accurate predictions. However, to confirm it, there was an extensive research for a matching particle associated with it, the Higgs boson. Detecting Higgs boson was experimentally difficult due to the energy required to produce them, and they break apart in about a 10th sextillionth, about 10 to the power minus 22 of a second. It was therefore several decades before the first evidence of the Higgs boson began to be found. Particle colliders, detectors, and computers capable for looking for such Higgs bosons took over 30 years, 1980 to 2010, to develop. By March 2013, the existence of Higgs boson was confirmed, and therefore the concept of some types of Higgs field throughout space is strongly supported. The nature and properties of the field are now being investigated further, using more data collected at the LHC. This is our picture of the discoverer of the Higgs field as well as the Higgs boson, Peter Higgs. Let us understand how the Higgs boson were produced and detected in the LHC experiment at CERN, Geneva. Production and detection. Higgs boson's production is detected among other methods in the invariant mass distribution of photon pairs or pairs of Z bosons. The latter ones decay in turn into lepton-antilepton pairs. The signal at a mass of about 125 GeV sticks out clearly above the background of other production mechanisms, which do not involve Higgs bosons. Indeed, we have there a second nice example of particle mass measurement through the invariant mass of its decay products. The measurements from the two experiments at the LHC give compatible results, which can be combined. This determines today the mass of Higgs boson to be 125 GeV with a precision of about 240 MeV, that is about 2 parts per thousand. This is a remarkable achievement by these experiments and is the fruit of the work of thousands of physicists and engineers during 2 decades. This is the data from the ATLAS experiment at CERN, Geneva. This proves the existence of the Higgs boson as well as the precision of 240 MeV. Now let us sum up the major properties of our Higgs boson and Higgs field. The Higgs particle is a well-established new particle. The probability that background fluctuates upwards to stimulate the signal is of the order 1 to 700 million. It is indeed a boson because its decay into 2 photons is observed. It very probably has a spin 0. Its couplings to different particles are indeed proportional. Now let us understand the major properties of the Higgs boson. The Higgs boson is a well-established new particle. The probability that background fluctuates upward to stimulate the signal is of the order 1 to 700 million. It is indeed a boson because its decay into 2 photons is observed. It very probably has a spin 0. Its couplings to different particles are indeed proportional to their apparent masses, as they should. Here we show a summary of results from the CMS experiment. We are thus sure that Higgs particle is indeed a Higgs boson. This, however, does not exclude the existence of other bosons of this type, which are obviously actively hunted by the experiments at the LHC. This is the data from the CMS experiment. So now we know the major properties of the Higgs field as well as the Higgs boson. Its mass was discovered as 125 GeV, which is neither 115 GeV, so that it may lead to our supersymmetry models, or not, nor it is 140 GeV, which leads to the multiverse theory. So the question remains still now, which way to go, supersymmetry or multiverses? In order to prove the existence of a multiverse or a supersymmetry, we need more precision, as well as further experiments are needed in order to confirm such an experiment. Now this picture shows us the present standard model of the elementary particles. As you can see, Higgs particles are included with the up charm, top, down, strange and bottom quarks, as well as the leptons, as well as the gauge bosons you can see in this picture. Now our idea of standard model is roughly a vague idea. We do have model which is enough to determine and describe the interactions of the nature, but there are particles, still there are particles out there in space, in our cosmos, the dark matter, the dark energy, and we think that probably dark matter, along with our present standard model, along with number of particles, are still a part of much bigger model. Well, in order to prove the existence of a bigger model, we need to find out whether there exist other particles like Higgs boson, which is going on. The experiments are still going on in order to find out such particles, and we need a lot of precisions and a lot of technological work out there. So this was all about the Higgs boson and the Higgs field. Thank you for watching this video. Hope you enjoyed it. Don't forget to subscribe.